Hello everyone and good morning. Welcome to Modern Semiconductor Devices for Integrated Circuits lecture number 2. We'll start with module number 1.1, that will be Semiconductor Physics Fundamentals. Today we'll briefly study about the evolution and uniqueness of semiconductor technology, and also will refer to the concept of equilibrium carrier concentration and thermal equilibrium. Rest of the topics will cover it, like for example wave particle duality, intrinsic versus extrinsic semiconductor, then the energy band diagram. These topics will cover it in the next lecture. Okay, and in module number 1.2 we have how does the carrier transport, random motion, drift diffusion, excess carriers, concept of injection level and carrier lifetime, direct and indirect semiconductors. So the other topics will cover in the subsequent lectures. So let us begin with today's topic, that will be semiconductor physics fundamentals. So let's start. Today's date is 17, and the first topic, the first point what we want to discuss is the importance of semiconductor devices. Importance of semiconductor devices. I guess in the last lecture we had briefly studied the classification of semiconductor devices, if I'm not wrong, correct? So these, yeah. So now these devices, the semiconductor devices, enhance performance, number one, reliability, and cost effectiveness of two systems. Okay, now which are the two systems which we are talking about? First is A part, energy systems. Okay, and the second category will be information systems. So semiconductor devices enhance performance, reliability, and cost effectiveness of energy systems and information systems. So what do you mean by energy systems? Energy systems will generate, distribute, and regulate electrical energy. Okay, so energy systems will generate, distribute, and regulate electrical energy. What is the aim? Aim of energy system is to manage larger and larger amount of energy and power. What do you mean by information system? Information system store, process, and communicate information. Okay, information system will store, process, and communicate information. What is the aim of information system? To manage large amount of information using lesser and lesser amount of power. Okay, so in brief, this is the importance of semiconductor devices, that it enhance performance, reliability, and cost effectiveness of two systems, which are energy systems and information systems. For energy systems perspective, we have to manage larger and larger amount of power and energy. For information system perspective, we have to manage the large amount of information using lesser amount of power. All right, now we'll next briefly see the course objective, the course objective of this subject. So let's write down Next, we'll start with the course objective. So basically, the course objective is there are two domains in this subject. We'll start about that now. The first domain is the terminal characteristics. First one of the devices. Terminal characteristics of the device. Under terminal characteristics of the device, we have DC IV characteristics. Okay, this is the important characteristics of interest. Then we have AC steady state characteristics. We can also call it as AC small signal. This is also IV. IV stands for DC current versus voltage, AC or a small signal current versus voltage. Alright. Then we have a third type, which is transient. Transient means current versus time, voltage versus time. Okay. So under terminal characteristics, we will be studying these three types: DC current voltage characteristics, AC current voltage characteristics, that is small signal analysis, and then transient current electrical parameter with respect to time, that is I of t or V of t. Alright. So for semiconductor devices, the important characteristics of interest are current through the device as a function of voltage applied. Alright. And the other part of it is, so this is one category of it. This is the first category. The second category is about material parameters, material parameters of the device. So what are the material parameters of the device? Let's list them down. Geometry of the device. Then we have doping levels. You heard of this doping levels? For semiconductors, we use impurities to change the concentration of electrons and holes. And this process is called as doping. I guess you have heard of it. Then we have energy gap, energy band gap. Then mobility of semiconductor devices. Then carrier lifetime. Actually, I'll just write lifetime. That means carrier lifetime. Carriers are electrons and holes in semiconductors. Then we have dielectric constant. Alright. So these are the list of material parameters of the device. Okay. Now there are two more third category also, which I am just mentioning it over here, which are ambient conditions. Depending upon the environment, the semiconductor devices also define certain properties. So they can change their uh, properties based on the applied temperature and illumination. When you shine light on some semiconductor devices, their property changes. So they behave differently. You all know about solar cell, right? Whenever solar energy is being captured, it gives out the output in terms of electrical power. Okay. So among all this, carrier lifetime is associated with small signal and transient response. All right. So what is the aim of the course? The uh, the course objective is relating. This is the course objective. The course objective is relating terminal characteristics of the device with material parameters of the device. Okay, mapping one by one. So the material parameter, there will be various devices, we'll just talk about them. So the material parameters of the device are geometry of the device, its length, width, dimensions, then doping levels, the amount of whether it's extrinsic, intrinsic, semiconductor, energy band gap, mobility, lifetime, carrier lifetime, and dielectric constants. And also the ambient conditions are temperature and illumination. So these are all the material properties of the device. Then our course will aim to bridge the gap between the two. Okay, so it will relate terminal characteristics of the device with material parameters. Now our focus of the course is, this is the focus of our course. We won't be studying in detail about the transient characteristics. We'll only concentrate on the DC current voltage characteristics and AC current voltage characteristics. Because for semiconductor devices, the important characteristics of interest are the current flowing through the device as a function of voltage applied. Alright, now let us see few examples of devices which we are talking about. So example number one will be a diode. All of us know about the diode, right? This is the symbol of a diode. It has an anode and a cathode. This is my anode and this is my cathode. Okay, the current flow in this from anode to cathode only. This is ID and this is plus minus VD. Now if I want to plot the terminal characteristics of this diode, how will it look like? I guess we have, I mean, you all know it by your previous knowledge of studying this device, maybe in your, grade 12 and even in school, right? So on the x-axis we have the diode voltage, on the y-axis we have the diode current, and how will be the characteristics like? In the forward bias, it will be exponential in nature. Am I correct? And in the reverse bias, it will be like this. Here it will be breakdown. So this kink means that you have a very large change in the voltage. So here we can see the current ID. This is the terminal current flowing through the terminals of the device. It's a function of voltage VD. Isn't it correct? Yes or no? So this is forward bias. This is reverse bias. And after this point, it is breakdown region. Okay. So here we have a breakdown region where the current starts increasing to a very, very high level. So these are the characteristics which we are interested in. The current flowing through the device as a function of voltage. Alright. So the application of a diode will be mostly in the rectifying. It can be used as a rectifier. Okay. In the breakdown region, it can be used as a stable regulator, like for example a Zener diode. So in a Zener diode, in a breakdown region, it will act as a stable um, regulator. Then the second one which we have is, are you understanding? Any doubts over here? This example number one. Students, any queries so far before I proceed ahead? You're following? Okay. Then the second type of a device which we'll briefly study will be bipolar junction transistor, which is BJT. Okay, this is my transistor. Now transistor, you will be soon studying it. Maybe in the last semester you might have heard of it, but we will be discussing it in detail. So it has three terminals. It is a three terminal, two junction semiconductor device. So this is my collector, base and emitter. Alright. So what it happens is, here we have input and output side. So base emitter side is my input side, VBE. So this is my input side. So input side we have a terminal voltage VBE and we have a current flowing into the device IB, base current. In the output side, this is my output side. So output side I have a current IC and I have a voltage VC, terminal voltage VC. Okay, so this is actually an NPN BJT. NPN BJT. So this is, let me add the terminals over here. This is N, P, N, O, NPN BJT. Okay. So here, why it is called as in NPN, what is the property? The current flows because of mainly electrons. The majority carriers are electrons. All right. Then here, if you plot the terminal characteristics, we will be studying this in detail, how we are arriving at this characteristics. Don't worry about it. So this is collector current versus VCE. Okay. So the characteristics will be something like this. It will increase and then it will saturate. Okay. And these are for increasing values of, these are all increasing values of IB. So this is IB1, IB2, IB3. So these are all increasing values of IB. Okay, base current. So here we can see this is a plot output characteristics. We call it as a output characteristics. Again, IV characteristics, right? So here we can also say IC is a function of VCE. This again comes under the category of DC current versus voltage characteristics. Okay, and the application of such a device will be amplifiers. Okay, your BJT normally it's preferred as a switch also, and it can be used as an amplifier also. So one of the applications of a BJT device is amplifier. So we'll study these kind of characteristics. All right, everyone. Yeah. So now let us look briefly into the devices part. Any doubt over here, students? Understood the course objective is to relate terminal characteristics of the device. We have seen two terminal characteristics. This is the first one, and this is another terminal characteristics. So during our entire course, we'll be studying about in detail these terminal characteristics of these devices and will relate it to the material parameters of the device like doping levels, energy band gap, mobility, lifetime. All right. Now next we'll briefly check the structure of these devices. So write down the semiconductor devices. The first structure is of PN junction. So PN junction will be made up of P-type semiconductor and N-type semiconductor joined together. So this is my structure for a PN junction. Plus minus, we will apply the external voltages. Then we have bipolar junction transistor, BJT. So in a BJT we have three terminals and two junctions. So here we have, here it is, let's say P, N, P. You can have variety of categories, but this is P and P. So here also we can apply voltages. It's the structure of these devices which I'm drawing. Okay, so here we have PNP where the majority carrier will be holes. So over here the holes from here will be going from the okay, these three terminals are emitter, this is the base, and this is the collector. So the holes will be traveling towards the base side. Since base is very thin, most of them will reach the collector, which is again a p-type material. Okay, so we'll study in detail about the devices a little later, but just now we are only checking the structure. All right, then the third device is MOSFET. What is the full form of MOSFET? Anyone? Yeah, metal oxide semiconductor is the most important device of the century. Field effect transistor. Okay, mostly in all our electronic devices we have MOSFET. All right. Now before MOSFET, we have to briefly check it out about MOSCAP. What is MOSCAP? MOSFET capacitance. Okay, so MOSCAP will be structure will be like this. So in your syllabus, you will be first study MOSCAP, MOS capacitance. So here we have, it has a, this is metal, M is for metal electrode, and P is for P silicon semiconductor, and this is an insulator. So this is SiO2 insulator. Okay, so it's like a parallel plate capacitor. We have two electrodes on two sides. It's a two terminal device. This is a two terminal device. Okay, so this is metal and this is substrate. So all right, so this is a MOS cap. This is metal electrode. Whereas if you here, in case of a MOS cap, we are only, the current cannot pass through the device. Why? Because of the insulator. This is my insulator, right? So if we want to say that the current is flowing through the device, it's not possible. So here the characteristics of interest are capacitance as a function of voltage. So because of SiO2, this is insulator. Okay. So because of SiO2 layer, it is insulator. There is no DC current flow. So here there is no DC current flow. Okay. Do you know memories, right? SRAM, DRAM, heard of it? Yes, memories in your mobile phone, flash memory, pen drives, all right, hard drives, external hard disk, all are memories. So what are they memories are made up of? They are made up of MOSFETs. So in those memories, we have stored. What is the role of a memory? To store charges, right? It is used for storage purposes, and you can read from the memory or you can write into the memory. So all these devices are also made up of MOSFETs. Okay, and this is the primary element which can be used for storage devices, MOS capacitor. All right. Now let's talk about the structure of MOSFET. So we have a MOSFET over here, similar structure, but with two fundamental changes. So here we have metal, then we have SiO2, and then we have P silicon. Same as this, right? But only certain differences there. So here in this pocket, here we have N plus, N plus. So basically this will be my gate terminal. It's a four terminal device. Gate, this will be, let's say, source, and this will be, oh, let me write it, this will be drain, source, or we can call it as, and this is substrate or body. Okay, so we, it is a four terminal device: gate, drain, source, body. As you can see, it's a slight modification over the MOS capacitor. So in your syllabus you will be first studying about the MOS capacitor, its features and everything else. So here, what is the process principle? So here there is a channel formed and the current flows like this in the device here. So this current I is controlled by VGS voltage, controlled by VGS, the voltage across the gate and the source. Okay, so if you apply the voltage across the gate and the source, this is VGS. It will control the amount of current which is flowing in this channel between the source and the drain. Okay, so we'll study about its features or its characteristics a little later. All right, but this is the structure. Got it? Everyone understood? Okay. Now we'll also talk about, since this course is about modern semiconductor devices. So in modern semiconductor devices, I have talked about heterojunction BJT, right? HBT, yes or no? So in a HBT, so here in a BJT, it's a homojunction. So that means P silicon, N silicon, P silicon. So all of them are made up of same material. In a heterojunction bipolar transistor, this is heterojunction. So in a heterojunction bipolar transistor, we have the same structure. So can you tell me what is the difference? I've explained this. P, N, yes, yes, tell. No, no. It's the same in BJT. In HBT, so here we use different material. Here we use different material. Here we use different material. Okay. So HBT is a variation of BJT. Okay, heterojunction bipolar transistor. So it has different applications. All right. So these are the devices which we are going to study in briefly in detail in modern semiconductor devices for integrated circuits. Basically, broadly, this is your syllabus. Your then we have optical devices also, but that is later. But major chunk will be PN junction, BJT, and MOSFET. That will cover around 80% of your syllabus. Okay. So let's start with the fundamentals. Yes or no? So we'll start with evolution and uniqueness of semiconductor technology. While the evolution part we have seen in the last lecture in motivation, now we'll see about the uniqueness of semiconductor technology. So let us start. Okay, so seeing the uniqueness of semiconductor technology, we'll first study the properties of semiconductor. So if you're listening so far, I'll recommend that you write down from now on. So first will be the properties of this very important properties of semiconductors. Why they are so versatile. So under properties we'll discuss four important properties today, which is polarity of charge carriers, polarity of charge carriers, then concentration of charge carriers, then we have transport of charge carriers, how are the charge carriers travel in a semiconductor medium. Okay, and then the next one will be interaction of semiconductor with a electromagnetic field. Interaction of semiconductor devices with electromagnetic, I am citing short form EM field. Okay, so these are the four properties of semiconductor devices which make them unique or semiconductors. Okay, note it down. Can I go and start with explaining one by one? Yes. Okay, so let us first talk about the polarity of the charge carrier. So can you tell me what is current actually? Current flow is due to current is no, it's flow of charges. So have you heard of this formula I is equal to dq by dt? So current is rate of flow of charges. Q is the charge, right? And t is the time. So rate of flow of charges will be current. I is dq by dt. So if there are flow of charges from one position to the other position, that means there is a current flow. Yes. Then let's talk about the polarity of charge carriers now. Let's talk about this point. So what do you mean by polarity of charge carriers? In metals, we have only negatively charged carriers, electrons, correct? So in metals, we have only electrons, and electrons are negatively charged carriers. Polarity of the charge carriers means in semiconductors, we have both the charge carriers, positive and negative. So we have positively charged. What are positively charged carriers called as? Anyone? Holes. Yes. And negatively charged carriers are? Yes, electrons. So in a semiconductor, we will encounter both electrons and holes. In fact, in BJT, bipolar junction transistor, we have both of them. It's other story key, one is majority, one is minority, but it's both of them present. So in semiconductor, we have two charge carriers, which one is positively charged carrier and one is negatively charged carrier, electrons and holes. Okay, agree? Understood about the polarity of charge carriers? So in semiconductors, there are positively charged carriers and negatively charged carriers in terms of electrons and holes. And in metals, we have only electrons. We don't have positively charged carriers. Any example of metals? Can you give me? Copper wires used for conduction of electricity, aluminium. Okay, so these are all metals which will have plenty of electrons for the flow of electricity. So electricity flow very easily through metals. Okay, next is concentration of charge carriers. Concentration of charge carriers. What do you mean by concentration? Anyone? Per unit area. Yeah, absolutely correct. So very interesting property of the semiconductor is that its concentration can be varied or can be changed over several orders of magnitude. Let me give you an example. So let's say that, let me draw this and show it to you, then you will understand. So x axis is my concentration of charge carriers. This is concentration short form, concentration of charge carriers. Okay, so here let me bifurcate this too. So this here the charge carriers are around 10 raised to 6 per cubic centimeter. Okay, the cc means cubic centimeter. Cc means centimeter cube or cubic centimeter. Here it is 10 raised to 21 per centimeter cube. Let me write per centimeter cube only. Okay, and this is my log scale, x scale. Why log scale? Because you cannot plot 10 raised to 6 and 10 raised to 21 on a linear scale. That's why we go for a log scale. Are you understanding? Now, where will insulators fit over here? These are concentration of charge carriers, meaning how many electrons and holes are present. So can you guess where will be? So there are three sections over here. This is section number one. This is second, and this is the third region. Where will be insulators? Any guesses? Insulators means what? The number of charge carriers are very small. Yes, so these categories of insulators. Where will be metals? Metals have yes. So metals have lot of electrons, so whose concentration is very high. And where will be semiconductors? Here. So what does that mean? So any material having low concentration of charge carriers will be termed as insulators. Any material which is having semiconductor material, or any other material or metals having very high concentration of charge carriers, especially electrons, will be called as metals. And for semiconductors, its concentration can be varied between 10 raised to 6 and 10 raised to 21. That's why we say its concentration can be varied over several orders of magnitude. Did you understand? So since we have such a large variation of concentration, we have so many electronic devices which are there in the market. All right. And then that's why we have so many applications of semiconductor technology or devices. Understood? This is the very interesting property of semiconductors, that its concentration can be changed or varied over several orders of magnitude. Understood, everyone? Yeah? Hello? Any doubts? Okay. Now, how do you achieve variation in concentration? Any ideas? I mean, how will you vary the concentration? Now we are saying semiconductors ka concentration can be varied between 10 raised to 6 per centimeter cube to 10 raised to 21 per centimeter cube. So how do we achieve that? So next question is, I'll ask, yes, one of the technique is doping. Any other? So let me write this question. How do you achieve variation in concentration? So first answer was doping. So that is called as by introducing impurities, right? By introducing impurities in semiconductor. And introduction of impurities in semiconductor process is called as doping. Correct. Any other technique? Can we say by changing temperature? Yes. So second technique is by changing the temperature. By changing the temperature of a semiconductor material, its concentration can be varied. Third, any guesses? By illumination, that is shining light. So by shining light on certain semiconductor materials, you can change its concentration. So these are the three techniques by which you can change the concentration of charge carriers. Yeah, number one, number two, and number three. Introducing impurities, by changing the temperature, and by illumination, that is shining light. All right, everyone. All right. Now we'll see the next property. So this is all about the concentration of charge carriers and polarity of the charge carriers. Let us revise. So in polarity, there is positively charged and negatively charged in the terms of electrons and holes. And concentration of charge carriers in semiconductor, unique feature is that its concentration can be varied over several orders of magnitude. And how do you achieve change in the variation in concentration? By introducing impurities in semiconductor, by changing the temperature, and by shining light. All right. Now let us go to the third one, that is transport of charge carriers. What do you mean by the word transport? Transportation means what? Transportation means how do the carriers move around in a semiconductor medium, right? How do they transport from one place to another? Correct? So there are three mechanisms over here. There are three mechanisms over here. Drift mechanism, please write them down. Very, very important to understand these things. Drift mechanism. Next is diffusion. How do the carriers travel in a semiconductor medium? First is drift mechanism, second is diffusion mechanism, and the third is thermoelectric current. Thermoelectric current. Okay, have you written? Okay, now listen carefully. Everyone with me? Okay, now listen, very, very important. These two are extremely important. The one I'm marking with yellow color. Here, these two. Because in majority 90%, more than 90% of them, semiconductor materials, the carriers travel either via drift phenomena or by a diffusion phenomena. So understanding this is very, very important. So listen carefully now. In metals and semiconductors, current flows whenever electric field is applied to it. Okay, remember, again I'm repeating, in metals and semiconductors, current flow whenever an electric field is applied. This kind of transport is called as drift transport. Okay, so whenever electric field is applied to the semiconductor material, the carriers travel via the drift phenomena. Okay, or else we can say, in a drift mechanism, the transport of charge carriers is because of potential gradient. Now, I'll explain it with an example. Don't worry about it. So write this statement. In drift mechanism, the transport of charge carriers is because of potential gradient. What do you mean by potential? Potential other name is voltage. What do you mean by gradient? Means difference. Potential difference or potential gradient. So transport of charge carriers is because of potential gradient. What do you mean by potential gradient? There will be high or low potential at different points of semiconductor. Yes or no? So there will be high or low potential at different points of semiconductor. The charge carriers traveling under such a phenomena, such a condition is called as drift. Okay. So here we can say from high to low potential differences. All right. Can I explain this with an example now? Okay, listen here. So let's say if you have a semiconductor material, N-type semiconductor material, let's say you have. So it's made up of N silicon. It's a silicon N silicon bar. Here are the terminals. Okay. And now you apply the electric field to it. Let's say you apply a voltage over here. External voltage. Okay. This terminal is A and B. The length of the semiconductor is L, small l. Alright. And the voltage which we are applying is Vs. Okay. So whenever we apply a voltage across a semiconductor, there will be a presence of electric field. Yes. So this, let's say this voltage is around, let's say 5 volt. So can I say here over here on this side we have 5 volt and this side we have 0? Yes or no? Hello, do you agree on this? Hello. So let's say this L is 5 units. I don't know, I mean this thing. So at this point the voltage will be, let's say 4 volt. At this point in a semiconductor, here over here, I'm just saying, giving an example. Here it will be 3 volt, here it will be 2 volt, here it will be 1 volt, and here it will be 0. So can I say at different points in semiconductor the potential is different? Yes or no? Hello. So what happens is the electrons will be attracted, will be repelled by the negative part of the battery, right? These are electrons over here, right? There are all electrons over here. So where they will go? Electrons, where they will go? Where they will travel? Whether they will go towards the negative part of the battery? No, because like charges will repel. So all of these electrons will travel to, will be attracted towards the positive potential of the battery. Yes or no? Agree? So all of them will be traveling from right to left. Okay. So when the electrons are traveling from left to right to left, so the current will travel from left to right. Okay, so current will travel like this, the opposite side of flow of electron, conventional current. Okay, now where is the electric field? All these electrons are traveling under the presence of electric field. So here is my electric field. This is electric field E. Remember one thing, if electric field is like this, electrons will go to the opposite direction of electric field always. So we have a very powerful electric field because of the potential difference. At terminal A we have 5 volt, at terminal B we have 0. And as we move along the semiconductor, the potential difference is varying. Okay, when you go from B to A, the potential is rising, and when you go from A to B, the potential is falling. Yes or no? From 5 to 0. Agree? So all these electrons, the means of transport of these electron will be drift phenomena. Okay, drift transport. You understood now? What is the drift phenomena? So electrons travel from a lower potential to a higher potential under drift phenomena. So this is due to potential gradient because there is a difference in the potential at different points of semiconductor. And electrons traveling under the influence of electric field will come under the category of drift transport. Are you agree? I mean, have you understood this? Okay, great. Now, let's talk about diffusion mechanism. Diffusion mechanism. So under diffusion in semiconductors, the current also flow because of diffusion. Okay, so here the transport of charge carriers, the transport of charge carriers is because of transport of charge carriers means the current flow. The current flow is because of concentration gradient. Concentration gradient. What do you mean by gradient? Change in concentration, right? Or concentration variation. Yes or no? So that is from high to low or and low to high concentration. Okay, so transport of charge carriers is because of concentration gradient. That is at one point piece of semiconductor material there can be high concentration of carriers. At other point there will be a low concentration of carriers. Yes, so the current flow because of such a scenario is called as diffusion phenomena. Yes or no? And in the possibility of diffusion in semiconductors, is it very high or very low? Can you tell me? Possibility of diffusion in semiconductors. Tell me if this phenomena is very high or very low. It's very strong. Why? Because just now we have discussed before that in a semiconductor material, its concentration can be varied over a large, variation of amplitude, large orders of concentration. So the possibility of diffusion in semiconductors is very strong in semiconductors. So you can have devices where we have low concentration of carriers and low and high concentration of carriers at the same time. So the current flow or the transport of charge carriers due to such a situation is called as concentration gradient. Understood this? Yes or no? Hello. So I'll give you an example. PN junction. Let's take PN junction. Is it okay? So here what do we have? Tell me. P silicon and here we have N silicon. They are both different materials, right? Yes or no? So here, what are the majority carriers in P-type material? Your majority are holes. And here majority carriers are in N-type. Can we say majority is holes but minority are electrons? Yes, yes or no? Here there are minority charge carrier electrons. And here there are minority charge carrier holes. So when you go from region P to region N, the whole concentration is changing, right, drastically. Your holes were majority, when you go to region N, they become minority. And similarly, when the electrons go from N to P region, holes are a majority in N region, but are a minority in P region. So there is a huge difference in concentration of carriers. Yes or no? Agree? So these holes may be in the range of 10 raised to 18 majority carriers. 10 raised to 18 per centimeter cube. And the minority carriers are, let's say, 10 raised to 4. Example I am giving. So this also per centimeter cube. So majority carriers are 10 raised to 18 and minority carriers are. So suddenly on the P side, the majority carrier hole concentration is 10 raised to 18. And when they go into the N side, the concentration reduces to 10 raised to 4. So there is a large difference in concentration. So the current flowing because of this diffusion process is called as diffusion transport. Understood now? Now let me also give you an analogy, okay, of this. Analogy meaning I'll explain you a situation where you have experienced this before. So you have a crystal clear glass of water, okay. You have a beaker, let's say, it's crystal clear, and you pour a water on it inside this. So it's filled with water. Now you pour ink on it, ink into it. What will happen? Will the water become entirely blue instantly, or what will happen? Can you describe? If you pour ink on a clear crystal glass of water? Yes. The phenomena by which the ink goes inside the water is called as diffusion phenomena. Agree? Or you are in a room in your house and someone has just sprayed a perfume. So you can smell the perfume from a distance also, from another room also, right? So the possibility, the process by which the scent travels from one place to the other place is called as diffusion again. Okay, so these are some examples which we use on daily basis, and this is a similar process to your diffusion process, what is happening inside semiconductor material, inside a PN junction. Okay, so two examples which I've given you. So the transport of charge carriers because of concentration gradient is diffusion phenomena, and this diffusion possibility is very strong in semiconductor materials, especially in semiconductor materials. Okay, I hope you have understood with the help of analogies also. Okay. Now in this curriculum, we will be studying focusing on mostly drift phenomena and diffusion mechanism. Then the third category, which we don't have, in this in the curriculum, will be thermoelectric current. Okay, the thermoelectric current. This is due to temperature gradient. So we won't be studying such devices currently. So let's say you have a semiconductor material, okay, and here at this side of the semiconductor, the temperature is T1, and on this side of the semiconductor, temperature is T2. T1 is greater than T2. Okay, whenever the temperature on the different sides, different points of the semiconductor are different, the current which is flowing is called as thermoelectric current. Okay, the example will be thermocouple. All right. So there can be situations that the temperature at different places in the semiconductor can be different. So the current flowing due to the temperature difference is called as, or temperature gradient is called as thermoelectric current. Now, have you all understood all the three transport mechanisms briefly? Yes, no? Okay, okay. Now that is what is uniqueness. So this is the property which we are after, the uniqueness. The uniqueness of semiconductor is that Here all the three mechanisms of transport exist. Okay, so here semiconductors, in metals and insulators we don't have all the three phenomena, but here all three transport phenomena or transport mechanism exist. And which are the three transport mechanisms just now we have discussed, everyone? Drift, diffusion, and thermoelectric current. So all three exist in semiconductors. That is why we can make different kinds of devices and we can have very interesting applications. So that's why we have so many devices and different applications in semiconductors, which has made this market the most sought out for in this century. Okay, and that's the uniqueness of semiconductor materials. We can have such wide range of transport mechanisms and properties, so we can build different kinds of devices, which very interesting proper characteristics. All right, everyone. Okay, now we have 5 minutes more. We'll talk, we have discussed about the transport. We have completed a discussion on transport of charge carriers. Now, last we'll have interaction of semiconductor with electromagnetic field. We'll discuss that briefly. First, let me give you a brief about drift transport. Drift transport. So, kindly, it is a drift velocity versus electric field. Capital E, when I write, it means electric field. So, if I plot a graph of drift velocity versus electric field, this is drift velocity. The velocity with which the carrier travel under the influence of electric field is called as drift velocity. Okay, so we have two curves. First curve is like this. Okay, and these, in most semiconductors we see such a behavior in elemental semiconductors. Okay, and there is one more curve which looks like this. Yeah, all right, and this is for compound semiconductors. Let's say gallium arsenide semiconductor or silicon, gallium arsenide semiconductor. This is basically for single elemental semiconductor. This is compound semiconductors, one or two materials. This is only made up of one materials. Okay, so this is electric field, x-axis. All right, so here you see, in case of uh, most of the semiconductor materials will see such a behavior, the red color curve. Okay, and one interesting thing to notice over here is, over the small electric field over here. Here there are small electric field, right? Both the curves are linear. Yes or no? Correct or no? Both the curves are linear, right? So for small electric fields, we have the relation. We have the following relation: the drift velocity upon the electric field is given by mobility. So we can say the drift velocity is proportional to the electric field for low electric fields. And what is mu? Mu is called as mobility of charge carriers. Mu is called as mobility of charge carriers. Okay, this is the information which I want to give you all. You have completed, you all have written it. This has a lot of significance. As you can see, yeah, the drift velocity will reach a saturation level. This has a lot of significance in MOSFET also. And there are two crust and a peak over here, right? So here there is this electric field is increasing and then it is decreasing. So what is this region in between called as? This region is called as negative differential resistance. This is the region of negative resistance. And these also have various properties, and we have devices, semiconductor devices will exhibit this phenomena, negative resistance region. This is negative resistance region. Okay, so this is a drift velocity versus electric field. So some compound semiconductor materials behave in this manner, and elemental semiconductor materials behave in this manner, like the red curve, mostly this silicon. And for small electric field, both of them, drift velocity remains proportional to the electric field, and the proportionality constant is the mobility. Okay, understood this? Okay. Next is, I just want to showcase one resistivity, resistance. So x-axis is resistance in ohms for different materials. So let me add over here. There are three boundaries over here. Here it is 10 raised to minus 3 ohms. Here it is 10 raised to 5. Can you tell me where will metal come? On region number 1, 2 or 3? Metal. 1, of course. Least resistance, right? Insulators, where they will come? Why? Because high resistance. High resistance means no current flow. Insulators doesn't allow any current to flow. And semiconductors, 2. Yeah. So again, for the semiconductors, we can have a large variation in resistance possible. Okay. So this is just the information which I wanted to give you all. For metals, how do you identify metals? Its resistivity or resistance is very low. Uh, Semiconductors, it can be varied in a large range, and insulators have a very high resistivity, very heavy resistance to the flow of electricity. Okay. Now the last point which I wanted to discuss was the interaction of, just 2 minutes more, interaction of semiconductor with electromagnetic field. Electromagnetic field or other form of energies. Okay. Here the first one will be discussing about the photoconductivity, or you can call it photovoltaic. Can you tell me what is the input and output in case of photoconductivity? Can you tell me? Input is and output is electrical energy. Yes or no? Input is light energy and the output is electrical energy. Now there is one more phenomena which is called as electroluminance. So in electroluminance, what is input and what is output? Yeah, electro means input is electrical energy and output is light energy. Can you give an example of such a semiconductor device? Yes, LED. And photoconductivity? Yes, solar cells, correct. So these are few examples of where you have, yes, yes, light dependent resistor. Yes, definitely. Yeah, LDR, right? Only thing is, in case of LDR, Whenever light falls on the LDR, its resistivity changes. Correct? Its resistance changes. When you connect that resistance in an electrical circuit, then the electrical energy will change. So there are three stages in LDR. From light energy to resistivity change, from resistivity change to electrical energy. Are you getting it? Directly it doesn't convert to electrical, intermediately it convert into electrical. So LDR will come definitely. Broadly it will come, but as I've explained you, from light to change in the resistance, from change in the resistance to, as I've already told you, electrical energy. Agree, everyone? So let me explain these two, and then I will be, that will be it for the lecture. So let me explain first. You have written, right? Interaction of semiconductors with electromagnetic field or other forms of energy. First is photoconductivity, and second is electroluminance. We have photoconductivity in your syllabus. Electroluminance, I guess we are not. I think we have it. Lasers also, right? Laser also comes into this category. Electrical energy in terms of light energy. Okay. So if you have a if you have an atom of semiconductor, so this is atom, and light wave falls on it. Light wave. Light wave means photons. Light wave falls on the semiconductor. It gives away electron and a hole pair. It gives away free electron and hole. So this process is called as EHP, electron hole pair generation. So this process is called as photoconductivity. We can say about LDR, as you have said. So whenever a light wave of frequency of particular frequency collides with an atom of semiconductor material, it breaks the bond, resulting in electron hole pair generation. Due to this, the conductivity changes because the energy is absorbed. Are you understanding? So in a LDR, for example, we use change in resistivity to detect light. Yes or no? So wherever there is a change in resistivity, that means we are detecting light. Again, I repeat, whenever a light wave of a particular frequency collides with an atom of a semiconductor material, it breaks the bond, resulting in it breaks the atom bond and resulting in electron hole pair. So light energy comes with there's a photon, and it gives away free electron and a hole. So there is a EHP generation, there is electron hole pair generation taking place. Because of that, the conductivity changes. Okay, of the semiconductor material. Understood this topic? Hello? Okay. This is photoconductivity. Now next, we'll talk about the photovoltaic, the solar cell. So whenever an electron and a hole meet in a crystal lattice, so free electron and a hole in a semiconductor, when they recombine, we can say when an electron and a hole they recombine in a particular semiconductor material, they give away light. Light has a particular frequency spectrum, right? So this is called as electroluminance. Example is LED, laser diode. So electrical energy to light energy. This is photon, which will emit light. You remember there are different colors of LEDs, right? Red, blue, green, yellow, ultraviolet also. So these depend upon the different materials. So whenever a free electron and a hole in a semiconductor material, whenever they recombine, they give away the energy as light. Agree? So in case of a solar cell, In the above example here, in case of a solar cell in photoconductivity, generated electron hole pair can give rise to a voltage. In case of a LDR, uh, because of the light, the resistivity of the material changes. And over here, in case of electroluminescence, if a free electron and a hole in a semiconductor recombine, energy is given away as light. Okay, so let me write this statement. A free electron and hole in semiconductor, when they recombine, energy is given away as light. Now, what is the color of the spectrum? What is the frequency of the photon? That depends upon the what color of the light is emitted. Okay, so these are the principles in laser diode and LED. Agree? Hello? Uh, Understood this phenomena of photoconductivity and electroluminescence? So that will be all for today. Give me 1 minute to revise what we have done so far in today's topic. Let me go back to the earlier slide. So we have completed today the evolution and uniqueness of semiconductor technology. Next lecture will start with equilibrium carrier concentration, thermal equilibrium, wave particle duality, and intrinsic and extrinsic semiconductors. So we have discussed about the importance of semiconductor devices uh, with respect to energy systems and information systems. Then we have related the course objective with respect to terminal characteristics of the device with the material parameters of the device. Then we have seen the structure of various devices which we are going to study in this subject, in this course, that is PN junction, bipolar junction transistor, metal oxide semiconductor field effect transistor, heterojunction bipolar transistor, and MOSFET also. Okay. Then we have seen the four properties of semiconductor, right? Now we have seen this also, right? The last one. Yes or no? So we have seen about the polarity of charge carriers. Semiconductor have two polarities, that is of charge carriers, positively charged and negatively charged in terms of holes and electrons. Then the concentration of charge carriers in semiconductor can be varied over several orders of magnitude, as we have seen over here. Uh, then how do you achieve a variation in concentration? By doping, changing temperature, or by shining light. Then we have briefly studied about the transport of charge carriers in terms of drift phenomena, diffusion phenomena, and the thermoelectric current. What was drift phenomena? Whenever there is an electric field present, there will be a change in the change in the potential, and whenever there is a potential gradient, the current flow or the charge carrier, transport of charge carrier means current flow. The current flow is due to potential gradient, is termed as drift phenomena. Now in a semiconductor, the concentration can be varied. There can be a change in the concentration from low to high or high to low. Just as an example in case of PN junction. So whenever the current flow because of concentration gradient, it comes under the category of diffusion. All right, and the possibility of diffusion is very strong in semiconductors. And the third scenario, due to temperature gradient. In a semiconductor, whenever the temperature is different at different points in the semiconductor material, come under the category of thermoelectric current. All right, and then we have seen the uniqueness of semiconductor material is encountering all these transport phenomena can exist. Then we have seen the drift velocity versus the electric field, and for elemental semiconductor and compound semiconductor, and we have seen the concept of mobility for small electric field. Then we have seen the interaction of semiconductors with the electromagnetic field. In the case, we have seen the two concepts of photoconductivity in case of LDR and solar cells, and electroluminescence in case of LED and laser diode. So in photoconductivity, we have a photon of a particular frequency, light, hitting a silicon atom, and it's giving away electron and a hole pair. So that is photoconductivity. And in case of electroluminescence, an electron and a hole in a semiconductor, when they recombine, they give away energy in the form of light. So that is electroluminescence in case of LED and laser diode. So yeah, that will be all for today. Next time we'll start with equilibrium concentration of charge carriers in semiconductor materials.